Hi, my name is Kylie Hansen, and this summer I worked on probing for super fast transients using Palomar Gattini-IR. I worked with Professor Mansley Kosliwal and Dr. Kylie. So for this presentation, I'll be giving a brief introduction as well as talking about data processing, photometry, image subtraction, and some general concluding remarks. So as an introduction, the tool that I used was Palomar Gattini-IR, or PGIR, which is a 30 centimeter near-infrared telescope with a field of view of 25 square degrees. The method that I used, so PGIR has a fast readout mode, which has an extremely short exposure time of about 0.82 seconds. And I used this mode to collect data of Nova V1674 Hercules, or from now on I'm going to call it Nova Her. I also used the data that I took of Nova Her to do some general surveying of the sky to look for random transients, which we will talk about at the end of this presentation. So this tool I used, PGIR, is an infrared telescope. So PGIR observes in the infrared section of the electromagnetic spectrum, and this is important because it allows us to see past all of the gas and dust that normally blocks our view in the optical light. So as you can see in the slide, there are two images. There's an image on the left of the Milky Way invisible light, or optical, and on the right is an image of the infrared Milky Way in infrared. So you can see here that all of the spots that are kind of obscured by gas and dust in the visible light are now very, very bright in the infrared. So we're able to see past all of these things, and that's pretty important because a lot of gas and dust obscures a lot of our view of the Milky Way, so we can see past all of that through infrared and potentially discover a lot of cool new things. Okay, let's talk about the method now. So before this project, PGIR's Fast Readout Mode had yet to be used to survey the sky. And also of note, the time resolution for the Fast Readout Mode is a factor of 10 higher than the normal mode. So this is an insane improvement on the time resolution. Also, what kinds of things might we detect with such a fast readout mode? So with such a short exposure time. So a few things. We might detect gamma ray bursts, which are theorized to come from small compact objects like magnetars and galactic microquasars. Or also the timing of compact binaries might be detected through the fast readout mode. And also cataclysmic variable stars. So this one is of probably the most important of these kind of things that I've listed here, because the nova that I observed, Nova Her, came from a cataclysmic variable star. So a cataclysmic variable star consists of this pair here on the right. There is a donor star and a white dwarf, and the donor star is feeding the white dwarf some material. And so because of that, that can lead to novae that explode and we see them in the sky. So that is what I observed. Nova Her is a cataclysmic is the result of one of these interactions with a cataclysmic variable star. Okay, so let's move on to the data processing. So once we have the raw data, we can't just use it right away. It needs to go through some processing before it's ready to be used. So let's go through this process here. You can see. First, we'll start with data collection. So we collected data using PGIR on June 15th, 16th, and 18th, 2021, this year. So you can see here a picture of our beautiful telescope, PGIR, and then also a image that it created. So PGIR's field of view is 25 square degrees, so 5 degrees by 5 degrees. So this is one of the images we actually collected. So this is what they look like. So once we collect that data, it needs to go through some processing. So the raw data is processed by first subtracting darks and then dividing by flats. So with the darks are actually applied as soon as the data is sent from PGIR to the Caltech server. But however, the flats are a different story. So a master flat is created every night, so I had to manually divide all of the images by that master flat. Once I did that, then I moved on to the astrometry, which allows us to know, to form a relationship between the pixels on the image and the sky coordinates. So in astronomy, we measure coordinates on the sky through right ascension and declination. And so astrometry allows us to calculate the relationship between those pixels on the image and the RA and dec, the right ascension and declination coordinates on the sky. So I performed some astrometry on it and was able to form that relationship. So once this processing process occurred, now we can move on to actually going towards that light curve through a process called photometry. So in photometry, there are two types. There's aperture photometry and there's PSF photometry. So we decided to use aperture photometry, and as you can see here, there are several things required for that. So you need to set an aperture radius, an annulus radius, and an annulus width. So in aperture photometry, you basically add up all the pixels within the aperture radius, which we set to 3 pixels. And then for the annulus, you basically use the annulus to calculate the background of your image. And then later on in the process, you'll subtract that background from the pixels that you all added up in the aperture to get kind of a real value for the flux of your source. So here you can see I highlighted in these green circles the aperture radius of 3 pixels, the annulus radius that we set to 11.5 pixels, and the annulus width of 3 pixels. So it's important that you set this annulus to be an area where there are no other sources so that you can have an uncontaminated background that you can later subtract. So that's what we try to do here. So you may ask, why use aperture photometry versus PSF photometry? And so I will talk a little bit about that. So aperture versus PSF photometry. So specifically for our work with PGIR, when we tried to use PSF photometry, it resulted in this weird kind of repeated pattern here that you can see in the light curve. This is the light curve. You can see it measures magnitude on the y-axis, which is a measure of brightness, and time on the x-axis. So you can see this repeated pattern here, and this is not something that we expected to see from the nova. So we were kind of questioning, why do we have this pattern here? And so we talked to some experts, and it was suggested that potentially there might be some issues with the consistency of the within each individual pixel. So if the sensitivity varies across individual pixels, then as the source kind of tracks across individual pixels, there might be this change in magnitude. So we decided to kind of delve into that and see if that was the case. So in order to look into that, we created these pixel maps. So what this pixel map is showing is on the x and y axis are just the x and y in pixels, and the color represents the magnitude or the brightness of the source. And so we did this for the nova and for a random star to kind of see if it would appear in both, and it did. As you can see here, the source appears brighter towards the edges of pixels and dimmer towards the middle. So the darker colors here are dimmer. So in the magnitude scale, larger values are actually dimmer. So you can see that there are kind of darker shades of red towards the middle of pixels and lighter shades of red towards the edges of pixels. And so this pixel map, the fact that it appeared in both the nova and a test star, a random star, shows that there might, or there probably is, an issue with the pixel sensitivity in individual pixels. So it's not, it actually varies across individual pixels, sub-pixel values. So that was kind of an issue with the PSF photometry. So that's why we decided to do aperture photometry, which doesn't deal with this issue as much. So once we did aperture photometry, we were able to finally create that light curve that we're talking about. So this is the light curve of Nova Her. So in the blue are the normal readout mode points, and in the red are the fast readout mode points. So let's just take a moment to appreciate the actual insane time resolution that we see here. So these very, very slim bars that you kind of see in red on the blue graph, part of the graph, actually extend out through these insets to be these kind of extended their own light curves. There's just so many points within such a short range of time. And so these are the 3 days that we took data. On the left is the 15th, June 15th. In the middle is June 16th. And on the right is June 18th. So on the right, we didn't actually take as much data on the 18th, so that's why it looks kind of more sparse. And in terms of these, we were looking for some structure, some short timescale structure in the Nova light curve. We didn't really find any. You might question, on this plot on the left, there appears to be some dips and other things. So let's talk about why we didn't believe that those were true. So this particular dip here is very, very big. So let's take a look at what that is. So this dip actually looks like this if you zoom in. And so on this plot on the left, there are 3 different light curves stacked on top of each other. On the top is the Lightcurve of Nova, and then the bottom 2 are just random test stars. And so if you see here, you can see all of the plots have the same feature. And so because they all have the same feature, it makes it kind of suspicious. It makes us think that perhaps it was just something to do with the detector or the environment. And so we looked at actually a difference photometry light curve. So what that is you take 2 different objects and you subtract them and form a new plot. And so for this, it was the light curve of the nova minus the light curve of the test star. And so you can see here that it forms this kind of light curve where it goes up in brightness and then drops in brightness and then comes back. And so this is indicative of a cloud actually passing across the detector. And so we tried subtracting multiple different stars, and they all performed, they all looked kind of like this in this pattern here. And so we decided that it was just probably a cloud forming this dip here. And we did this process for all of those kind of dips and wiggles in the light curves and kind of ruled each of them out. So some of them were caused by the telescope slewing, which kind of smeared out the stars or, other clouds and things. So unfortunately, there were no features in the short timescale light curves. Now that we've talked about Nova Hercules, let's now move on to the second part of my project, which has to do with looking for random things in the universe, basically in our galaxy, through the short timescale exposures that PGIR's Fast Readout Mode can provide. So in order to do that, we need to use image subtraction. So how do we find transients that we don't know are there already? So for example, with the nova, we already knew where the nova was, and we were able to just point our telescope there and measure the nova and look for short timescale structure. But what if we don't actually know where the potential transients are that we're looking for? So we use image subtraction for that. So the image subtraction process goes like this. So first you create a reference image using this program called Swarp. So what Swarp does is you feed it a stack of images that have really high limiting magnitudes and combine those using clipped mean stacking. And it combines those using clipped mean stacking, which basically means it gets rid of the outliers of those images in order to make just a general reference image of really high resolution. And so once you have that reference image, you convolute, you go through this convolution process. So you cross-convolute the PSF of the reference image, so the point spread function of the reference image, with each data image, and then the other way around. So you use the PSF of each data image to convolute with the reference image. And so once you do that convolution, then you can subtract the data images and the reference images to create this difference image. So once you do that, you are presented with 2 different files. Swarp gives you 2 different files. So you're given the score image, and then you're also given the difference image. So the difference image is actually the result of that subtraction. And the score image is the statistical relevance or significance of the pixels in the difference image. So the score image will tell you, hey, is this, bright spot here statistically significant in the difference image? And if it is, then it'll appear as such in the score image. And so in order to find sources through image subtraction, we run a program called source extractor on the score image. So what source extractor does is it can find, it is built to find sources in images. As simple as that. There are actually a lot of different parameters and stuff that go into source extractor, but that's as simple as it gets. And so once you run source extractor on the score image, you can find different sources and potentially find those transients that you're looking for. Unfortunately, when I ran source extractor on the score image, it ran into some issues. So as you can see here, bad pixels cause false sources. And unfortunately, with our science images, they have a lot of bad pixels, especially in this particular region here that you can see I kind of highlighted. On the left is one of the score images, and on the right is kind of a zoomed in view of that area of the score image in the science image. So as you can see here in the science image, there are tons of hot and dead pixels, bad pixels in general, in this area, and it results in false sources in the score image. And so because there were so many of these bad pixels, it was causing a lot of kind of unnecessary or false sources in the score image that source extractor was picking up. So one of the things that I'm working on to kind of combat this is to run source extractor on the science image as well as the score image. And so if source extractor can find a source in the science image that's in the same location as the source in the score image, then we can possibly say it might be a transient. Because if it was a hot pixel, source extractor would not detect hot pixels as sources. So where a hot pixel is on the science image, it would say there would be no source for when source extractor was run on the science image. But if source extractor found a source in the score image, I could tell it then that that source in the score image is not a real source. So that's potentially what I'm working on currently to try and solve this issue with the bad pixels. Fortunately, there is some good news. So other than those false sources that source extractor finds, I manually looked through the score image to try and find some real sources. And there are real sources, actually. So with this particular set of images here, on the left is the score image and on the right is the science image. You can see that the score image has this source here, and there isn't a bad pixel where it would be on the science image. There's an actual source there. So we took a look at this, and I made a light curve for it. So you can see here, this is the light curve of this source found in the score image, and it has this weird kind of drop in brightness and then carries on. So it actually did change in brightness, and so the value we saw in the score image was correct. It actually is a source. It's not just a bad pixel. So that was exciting. So there are a few more of these that I manually discovered by just looking through the different images, the score images. And so the image subtraction does actually work despite the bad pixel problems that we have to deal with. So in summary, some concluding remarks. So PGIR's Fast Readout Mode, I used it to look for short timescale structure in Nova Her's Lightcurve. Unfortunately, we didn't find any, but we did discover that the PSF Photometry could not be used due to changing sensitivity across individual pixels. We discovered there was this problem here, which is good to find, even though we didn't really find any short timescale structure that we were looking for. Also, I used it to look for short timescale transients through image subtraction. And two things with that. We discovered that bad pixels litter the science images, which create false sources in the score and difference images, unfortunately, that we have to deal with, which I'm currently working on. And also found a real source that I presented to you earlier, and there are multiple of those, so there's some hope on the horizon. So moving forward, some questions we might ask: why did we not find any short timescale structure in the Nova Her Lightcurve is unknown. It's kind of strange. Also, how do we disqualify the sources caused by bad pixels from the score image? So I talked about a method that I'm trying for that, but if that doesn't work completely, then we might have to try and think of other, more creative ways. Also, what are the causes of the real sources that we found? We also have to think about that. And excitingly, I will potentially be working on this in the fall at MIT. Many thanks to Professor Manfred Kaziwa and Dr. Kisha Leja that I worked with this summer, as well as the Caltech WAVE program for allowing me to do this research this summer. Thank you for watching my presentation, and I'll see you for questions later.